Okay, so we're going to continue on the next problem that's on the handout. I'm recording the class today because there are a few people that are going to make it for whatever reason, some reason, different reasons. So what we're looking for here is the interval of convergence and the radius of convergence. I guess not necessarily in that order. So there's that buzz. So again, what we do is we let the whole expression be this u sub n, including x, the x term. So you change n to n plus 1. And I'm just going to go ahead and simplify them. You know, once you put n plus 1 in for n, you'll get n plus 2 where there's n plus 1. So it's n plus 1, which is n plus 2. And then you use the ratio test. So you take the limit as n goes to infinity of the absolute value of u sub n plus 1 divided by u sub n. And we've already written down what those are. So you'll have x minus 2 to the n plus 1 divided by n plus 1. Oh, sorry. Got the wrong ones in there. N plus 2. So it's u sub n plus 1 first. So x minus 2 to the x minus 2 to the n plus 2 divided by n plus 2 times 4 to the n plus 2, all divided by x minus 2 to the n plus 1 divided by n plus 1 times 4 to the n plus 1. So why don't you guys go ahead and simplify that as per the previous problems that we've worked on. So what happened over in Buena Vista? It rained a lot last night?
Okay, yeah, we had really bad rain. So in Long Hollow, it entirely flooded. And like where they do road work, there's a plate. So the rain took the entire plate out. Now there's a hole inside the road.
Oh, really?
Yeah, it's
Is
on
it?
my side of Buena Vista. We couldn't even get down the hill because I live on giant hill. So if
Yeah.
we went down, the entire river was flooded right there. So we
Oh.
couldn't leave.
Yeah, I saw some pictures on the news last night.
And those people they had their floats in the river. Like they were swimming in the river while it was flooded.
Really? Crazy. Yeah, I practiced, gone working on my choir. Our cantatas this weekend, and as you can tell from my voice, wasn't in singing form, so I just stayed home, which, oh well, that's life. I think my mind's kind of in a fog this morning. I don't know what it is. Now, I found to keep these things straight, I'm going to undo here, but then I'm going to redo. Sometimes it's better to just write out the terms that are in the numerator and just kind of separate them out. So you have x minus 2 to the n plus 2, that's in the numerator. Then this one is in the denominator, and then you've got this one that's in the denominator. I went ahead and did this one because I was matching those up. But once you've gotten the numerator in there, the use of n plus 1, then it's easy to put the others because you know they have to match up. They're always ratios, so you should never have them in the same position. And then you use the properties of exponents. Whoops. So we get our usual thing. We get a range of numbers. Our radius of convergence is this number here. That's how far you go either side of your center point. This original series was centered around x equals 2 because anytime you have x minus plus or minus something, whatever that number is that makes that term go to 0, is the term that the series is centered around. And you can see how x is centered around 2 goes plus 4 and minus 4. And the radius of convergence is always the same on either side of the center point. Of course, we don't know what the endpoints are until we plug in the n values. So we're going to plug in x equals negative 2 and x equals 6 into the original series to then check the endpoints to see whether this works at negative 2 and at positive 6. So let's find the equation again because I've already forgotten what it is. So there's the original series. So what you do is you plug in x equals negative 2 and you plug in x equals 6. And then you look at the, so see if you can simplify those down. Remember what we've done in the past is if you have, this is not this particular problem, but if you had negative 2 to the n, that's negative 1 to the n times 2 to the n. You can always break that up into negative 1 because you're going to, that way you'll end up with an alternating series. And then think about what the one end will be an alternating series, the other end will not be an alternating series. But you should be able, once you've made that substitution, this should simplify down considerably. Yep.
Do you have another one of these packets?
I don't, because I gave it, you know, you didn't get one? Okay, because I gave it late last week sometime. We were working on it on Friday.
I wasn't here Friday.
We were working on it Thursday. Pretty sure we did. Or was it just Friday? I'm pretty sure I handed that out before then. Anyway, I don't have a copy of it. Yeah, I think I handed it out Thursday, but we didn't work on it yet. So.
You said you had extra.
Did I? Yeah, I didn't bring any with me, so. I can get you one between classes, but. Oops. So once you've substituted -1 to the n times 4 to the n, well, -1 to the n plus 1. So this will become -1 to the n plus 1 times 4 to the n plus 1. But the 4 to the n plus 1's cancel out, and what you're left with is n plus 1. So if you didn't, I skipped from here to the answer. So go ahead and fill that in if you didn't do the intermediate steps. The same way down here, if I simplify this, I get 4 to the n plus 1. So I don't get this alternating sign result. I'm just left with 1 over n plus 1. And this one converges, and this one diverges. So I'm going to ask you guys why that's the case. Pull out your sheet of tests, and you can tell me. We've seen these before. What you would have to do to prove it is true. So, Vanna, what's the first series there? The one that converges, what kind of series is that? So do you see any that have -1 to the, yep. And so what are the convergence criteria for that?
The limit has to equal 0.
Yes. Does the limit equal 0? Yeah. And a sub n plus 1 has to be less than a sub n. And you would, if you put n plus 2 in for n plus 1, and, you end up with that ratio. So what Van is saying is that if you look at the non-alternating part, which is 1 over n plus 1, as n goes to infinity, it's going to go to 0. So that satisfies one part of the alternating series test is this. So the question is, does the limit of 1 over n plus 1 as n goes to infinity equal 0? And the answer is yes. And the second part is a sub n plus 1, which would be 1 over n plus 2. Is that always less than 1 over n plus 1? And if you cross multiply and eliminate the n's, you get 1 is less than 2, which is always true. So that's why that one converges. So Tristan, why does the second one diverge? You have any idea which test you would use for that? Let me ask you, would 1 over n diverge? What kind of series is 1 over n? Yes, we're comparing. What kind of series is 1 over n? P series, yeah. So, I mean, we see that a lot. So, anytime you see 1 over n plus 1 or minus 1, you can either use the direct comparison test or the ratio, limit comparison test. And in this case, because, well, in this case, you'd actually have to use the limit comparison test because in this case, this diverges. So just because 1 over n plus 1 diverges doesn't mean that because 1 over n diverges doesn't mean that 1 over n plus 1 diverges, even though it's most likely it does. But it's in that case, so we'd have to use the limit comparison test because that says that if the limit is equal to some value L and b sub n plus 1 is always less than a sub n, then the thing diverges. So it kind of depends on which way you think it's going. Is it going to diverge or is it going to converge, just based on looking at what the simplified expression is. So if we had 1 over n squared plus 1, we could use the direct comparison test because 1 over n squared would converge and 1 over n squared plus 1 would always be less than 1 over n squared, so that would mean that it would satisfy those requirements. But in this case, because 1 over n is the result, the thing that we're comparing it to, we'd actually have to use the limit comparison test. So pull out your sheet again. I'm going to get my book, look at the description. So the limit comparison test says, well, actually, the limit comparison test is a little easier because you don't have to. Only thing that has to happen is a sub n and b sub n have to be greater than 0. So what we would do is you set this limit up. Limit as n goes to infinity. So I'm just looking at the convergence thing. You know, we're looking at a sub n over b sub n. In our case, b sub n is 1 over n. And we know this diverges because it is a p-series. And with p, so now we go to the p-series, it says p, if p is less than or equal to 1, then it diverges. So this diverges, and if I take the limit as n goes to infinity of a sub n was 1 over n plus 1 divided by 1 over n, which is the same as n over n plus 1. And you can see that's one of those cases where you've got the same order in the numerator and the denominator, so that equals 1, which is equal to some finite value. So that's, as long as this is anything that's not infinite, it could be 0, it could be 1. As long as this equals a number, then if b sub n converges, then a sub n converges. In this case, b sub n diverges because it's a p-series. Okay, so that's kind of a lot of the endpoints in these kinds of series are P series or alternating series. So you should get familiar with those cases. A lot of times they simplify down to fairly trivial series because a lot of the stuff cancels out when you go to the endpoints. Okay, so there's section 8 homework. If I assigned that already, I don't remember. Probably not. So that's due. Let's say it's due Friday. Well, Friday, Monday. Monday, since you guys from Bath County are gone till Monday. Now we got one more problem on the handout, but we don't know how to do that yet. So. Okay, so let's move on to the next section. I'm trying to remember what I'm doing here. Yeah, section 9. I think I'm going to come back to. We're going to skip over that for right now. We're going to go to section 10. Section 9 is kind of an oddball. So we're going to look at section 10. And really it's the same as section 7, except these are infinite series instead of finite series. So it's basically using the same technique that we used for finding series with finite number of terms and having an infinite number of terms. Now that we have an infinite number of terms, then we need to determine whether it converges or diverges. So it's somewhat of a rehash of what we've already done. I do want to actually, I have something else I want to try here. So let's go back to what we just did. I want to look at that problem we just finished working to demonstrate how this whole thing works with this interval or radius of convergence. So what I want to do is to put together a spreadsheet, and that's a good time for me to take roll here. Let's see, they're dancing, or they were dancing. Okay. So what I'm going to do is I'm going to create this series, and I'm going to evaluate the series at different values of x and see what the behavior of the terms. So this is going to be n. We're going to start at n equals 0, and we're going to increment n. So we're going to do 25 terms of the series. And we're going to try values of x equals 1, 2, 3, 4, 5, 6, 0, -1, -2. Now, actually, I'm going to have to probably insert a row here between each one, or a column between each one, so I can do the calculation as far as summing the terms together. Well, I'm going to actually delete that, get rid of a few of these. Okay. So these are going to be a sub n, and a sub n is equal to x minus 2, so it's going to be equal to x is this number, minus 2, raised to the n plus 1 power. Here's n plus 1. So that's x minus 2 raised to the n plus 1 divided by n plus 1 divided by, again, 4 to the n plus 2. 4 to the n plus 1. 4 raised to the n plus 1. So this is at x equals 1 with n equal to 0. Let me just double check this. X minus 2 to the n plus 1 divided by n plus 1 divided by 4 to the n plus 1. Okay, push enter. And so I'm going to copy that formula down. And then I'm going to do that for all of these. You can see a sub n, as n goes to infinity, approaches 0. Something's wrong there. What did I do? Oh, I know what I did. I've got to change my formula a little bit here. I want to keep the column the same. So if you want to keep the column the same, but let everything else increment, then you put a dollar sign in front of there. So that should work now. These don't change. But when I copy this over here, it should look better. Yeah. Okay, so I'm just going to paste this formula. And you can see all of them go to 0 as now they're not changing at all, so I've apparently done something crazy there. What did I do here? Oh, I know what I did. I need to change this one. Let's see. Take the dollar sign off of there. Yep. Now it'll work. Sorry. Okay, let's see if they change. We should get a different result now. Didn't like that either. Now I'm still messed up here. What am I doing here? Oh, well, x minus 2, you get 0 to the something power. Interesting. Well, let me see. Oh, that's okay. Yeah, that's because that's the midpoint. That's why it's doing that. You'll notice that if you look at x equals 1 and x equals 3, this one's a non-alternating series, this one's an alternating series. So those look similar, but they're not the same. There is some symmetry to how these things work. That's why you get a radius of convergence that is symmetric around the center, because you always get kind of a symmetry. So if I add these terms up, so now what I'm going to do is I'm going to take the first term, and that's just going to be the first term, and then I'm going to take the first term and add the second term to it. And then if I keep doing this, it'll just keep adding them together. and we see that, you know, it starts approaching a fixed value. So it's converging here at it's converging at x equals 1. It absolutely gets converged at the point of the center because it's 0. And if I paste all these things in here, and I look at the behavior, you can see how these are all approaching some fixed value. But if I come down to the two values of x, which are the limits of the interval of convergence, one of them is going to converge, which is this one that's this alternating series. It will, whereas this one's just getting bigger and bigger and bigger, even though it's doing it slowly. It is continually climbing. And if I would change this to, say, 7 instead of 6, which is outside of the interval of convergence, you'll see that the value just keeps getting bigger and bigger and bigger. You know, it absolutely doesn't converge. All these other ones that are inside the interval of convergence are approaching some fixed value. You can see how they're all, after 25 terms, they're essentially constant. But if you have an x value which is outside of the interval of convergence, you can see how the sum just gets bigger and bigger. So it's obviously diverging here. Now when it's right at the limits, at the ends of the interval of convergence, then it's very questionable. It turns out that this one's converging, the one that's the alternating part, even though it's converging very slowly, but the one that is the other side, the -2 side, or the +2 side, pardon me, the positive side, x equals 6, that one is growing continually. Anyway, I was trying to demonstrate how those things work, so what's going on. So it's saying that series converges. So what's the difference between Taylor polynomials and Taylor series and Maclaurin polynomials and Maclaurin series? Nothing, except one has an infinite number of terms and one doesn't. So let's do an example here again. But in this case, we're going to come up with the infinite series. We're going to find the natural log of x, a polynomial approximation for the natural log of x. We're going to center it around x equals 0. The reason we're doing, x equals 1, because if we take the natural log of 1, we get 0. If we did it around x equals 0, the natural log is not defined for less than 0, and at x equals 0, the function goes to -infinity. So it wouldn't make much sense to do it around 0. So it's going to be a Taylor series. So what you do with either a Taylor series or Maclaurin series is you take the original function and you take the derivative, and then you evaluate the derivative, all these derivatives at the value of x, which is the center point. So this is my original function, the natural log of x. So I evaluate that at x equals 1. The natural log of 1 is 0. If you take the derivative of the natural log, you get 1 over x. Now that's the same as x to the -1 power, so if you take the derivative of that, you get -1 over x squared. That's the same as -x to the -2 power. So then you get, the next thing you get is 2x cubed. Next one is -6x to the 4th. And if you plug in the value of the function, well, if you plug in the value of x into the derivatives for each one of these, you get the first derivative at x equals 1 is 1. The second derivative is -1. The third derivative is +2 factorial, 2 times 1. The fourth derivative is -3 factorial. So you can see the pattern that's emerging here. So if we wanted to write the Taylor polynomial, so we'd say p of x. Well, actually in this case, we don't use p of x because we're going to have an infinite number of terms, so it is actually f of x. It is a polynomial, but it's going to be exactly equal to f of x. So it's going to be 0 plus, that's f of 1. Then you take the value of the first derivative, which is 1, times x minus 1. And we're doing x minus 1 because we're centered around x equals 1. Then the next term is going to be negative 1 times x minus 1 squared. And the next term would be plus, oh, and this is divided by 2 factorial. And that comes from the fact the Taylor series is f of 0 plus f prime of 0 times x minus 1 over 1 factorial plus f prime of double prime of 1 times x minus 1 squared over 2 factorial. So the next one we'll get a positive 2 factorial times x minus 1 cubed over 3 factorial. And then the next term is negative 3 factorial over x minus 1 to the 4th divided by 4 factorial. And you know, we see the pattern now. It's going to be plus 4 factorial times x minus 1 to the 4th over 5 factorial. And then you have minus 5 factorial times x minus 1 to the 5th over, yeah, messed up there. Wait a second here. 1, 2 factorial, 3 factorial, 4 factorial, 5 factorial, 6 factorial. Okay. Dot, 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 dot. And then you have the nth term, but before we do that, what you can do is 2 factorial divided by 3 factorial, or 3 factorial divided by 4 factorial. What happens, let me just show you that. If you got 2 factorial over 3 factorial, that's the same as 2 factorial over 3 times 2 factorial. So I expand 3 factorial out as 3 times 2. Those cancel out. So this infinite series is going to be x minus 1, 1 times x minus 1, minus x minus 1 squared over 2. So 1 factorial divided by 2 factorial is 2. The next term will be x minus 1 cubed over 3 minus x minus 1 to the 4th over 4 plus x minus 1 to the 5th over 5, etc., etc., etc. So all these factorial stuff can be simplified down. And if you look in your book, and actually it's on the back of the sheet I copied that has the convergence tests. If you turn that over, you'll see that there's this page in the book. Right? And these are the power series for elementary functions. And you'll see the natural log of x is equal to x minus 1 minus x minus 1 squared over 2 plus x minus 1 cubed over 3 plus x minus 1 to the 4th over 4 plus dot 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 negative 1 to the n minus 1 times x minus 1 to the n over n. Okay, so they come up with that formula, and they say that the interval of convergence is between 0 and 2, not including 0, but including 2. So what we have done there is we have derived the infinite Taylor series representation of the natural log of x centered around x equals 0. And they're telling us what the interval of convergence is, but let's go ahead and practice that again because you guys still need some help. What you would do is you would look at this series, the summation, now that we have it in equation form. That's one of the purposes here of using the Taylor series representation is to write it out and then try to figure out. Now you're not going to have to do this, but if you were, if you were the guy developing this stuff, then you would have to deduce what this formula is. It's not like it's impossible or anything, but so this is what the formula looks like. So let's apply the techniques we've been talking about. So u sub n plus 1 would be equal to negative 1 to the n minus 1, well, n plus 1 minus 1, right? So it's to the n plus 1 minus 1, x minus 1 to the n plus 1 divided by n plus 1, and u sub n is negative 1 to the n minus 1, sorry. And one of the questions is does this work? Does it start at n equals 0? I'm not sure, but let's not worry about that right now. X minus 1 to the n over n. Okay, so there's u sub n. Here's u sub n plus 1. So we take the limit as n goes to infinity of the ratio of negative 1 to the n. So this is n plus 1 minus 1. So it's just negative 1 to the n times x minus 1 to the n plus 1 over n plus 1 divided by negative 1 to the n minus 1 times x minus 1 to the n over n. We don't have to worry about the negative signs with the absolute value. That's supposed to be less than 1 to find our radius of convergence. If we simplify all that stuff down, we'll end up with, we're going to drop the negative 1 to the n because we have the absolute value to kind of wash that out. And you have x minus 1 to the n plus 1 over x minus 1 to the n from these two terms. And you have n plus 1 here in the denominator, so this one has to go in the numerator. And you can see that this simplifies down because of using the law of exponents down to x minus 1. X minus 1 to the n plus 1 divided by x minus 1 to the n is just x minus 1 to the first power. And then we have n over n plus 1. If you take the limit as n goes to infinity, this becomes 1. So we get x minus, absolute value of x minus 1 equals 0, or negative 1 x positive 1. I went too many steps there. Let me. I skipped a step. So what we get is, what do we want to do here? Oh, it's because I wrote this wrong. I'm like, what am I doing? This is 1. So what we say is x minus 1 is greater than negative 1 and less than 1. So that's how we handle the absolute value. And then if we add 1 to each element here, we'll get 0, x, and 2. Okay, so you can see that agrees with what we have on our chart, except we have to worry about the endpoints. So we're going to evaluate the original expression at x equals 0 and at x equals 2 and look at the convergence of that situation. So let me grab this thing and move it so we can see it. Okay, now what we're going to do is look at the endpoints of our interval. So we're going to do where x equals 0. And so we have the summation from n equals 0 to infinity of negative 1 to the n minus 1 times 0 minus 1 to the n, all divided by n. And because we have the same negative 1, we can add the exponents. So we'll have negative 1 to the 2n minus 1 over n. But this is always going to be odd, because if n is equal to 0, you get -1, and if n equals 1, you get +1. If n equals 2, you get 3. So because of the fact that this is always odd, the summation simplifies down to the summation from n equals 0 to infinity of -1 over n. And that diverges because it's a p-series with p equal to 1. Okay, so that's why it doesn't work at x equals 0, because these two combine into such that it is not an alternating series. Now if I plug in x equals 1, what I'll end up with is an alternating series. So here x equals 2. So when you plug in x equals 2 back into the original series, you'll get -1 to the n minus 1 times 2 minus 1 to the n divided by n. But this is 1 to the n, not -1 to the n. So this one will end up just becoming 1 to the n, which is always 1. So once you take that into account, then this thing simplifies down to -1 to the n minus 1 over n. And this is an alternating series. And it converges for the same reason the other alternating series converged earlier, because the limit is 1 over n as n goes to infinity is 0, and if I plug in n plus 1, a sub n plus 1 is always less than or equal to a sub n, and so it passes the two requirements for the alternating series test. This one was not an alternating series, it was just a p-series, and as a consequence it diverged, and that's why you see in the book that this particular series representation for the natural log of x has that particular interval of convergence. Okay, so that what we're going to do here is we are going to continue on just developing these, practicing this whole idea. We'll look at the sine and the cosine, look at their series representations. We'll do the convergence test. In that case, if you look at that sheet of paper, it says that the interval of convergence is all real numbers. So we will have to show why that's the case. And we'll do that tomorrow.